Hello, and welcome to an intro to self-driving cars. My name is Jane Shepard, and I'm the head of alumni here at Udacity. Today, we're exploring the world of self-driving cars. You've probably heard of them, might have seen one or two, and maybe even had the chance to ride in one. But do you really understand how self-driving cars work? Well, you're about to find out. Today, we welcome David Silver, product lead for Udacity's self-driving car nanodegree programs. David will explain how self-driving cars work and share his insights into how these amazing vehicles will change our world. And then he'll explore some of the jobs available to self-driving car engineers. Please welcome David Silver.
Hello, world. Hi, everybody. It's nice to talk with you. Good morning, or at least it's morning here in California. I'm really excited to share with you both how self-driving cars work and what's going on with them in the ecosystem, in the wider transportation ecosystem, and what jobs you might be able to get working on autonomous vehicles. I'll start by just telling you a little bit about who I am. So my name is David Silver. I lead the self-driving car team here at Udacity. I've been at Udacity for about 2 years. I came here to build the self-driving car program. I came to Udacity from Ford Motor Company, where I was on their autonomous vehicle team in Palo Alto, California. And before Ford, I was for many years a normal Silicon Valley web software engineer. I don't know if any of you know what this red icon here on the slide is, but that's Ruby. I was a Ruby on Rails engineer. That's a particular programming language and framework that's popular for web applications. And a few years ago, I got really excited about self-driving cars, but I didn't have any background in automotive software or robotics. So I started taking classes online about perception and machine learning and system software, and eventually I was able to get that job working on autonomous vehicles at Ford, and the folks at Udacity asked if I would come here and build out for other people essentially what I'd done for myself, a path to working on autonomous vehicles. So it's been a terrific ride, and we've had over 12,000 people now take our self-driving car nanodegree program. And I'll tell you a little bit about how self-driving cars work and what the nanodegree program covers. First, one other thing I should mention about Udacity is Udacity was founded by a man named Sebastian Thrun. Sebastian was a professor at Stanford University for many years. He led the Stanford University team that won the DARPA Grand Challenge, big 100-mile self-driving car race through the California desert in 2005. And then Google hired him to launch the Google self-driving car project, now known as Waymo. And he was at Google for many years working on that. And eventually Sebastian wanted to get back into education, so he launched Udacity. So Sebastian's a really interesting person for me to be able to work with. He's kind of the father of the self-driving car, and it's a real honor to get to build out the nanodegree program with him. So you're learning from some of the best experts in the world about how self-driving cars work. So at Udacity, we have our own self-driving car. Her name is Carla. And the final project of the nanodegree program is, in fact, that students get to put their own software on Udacity's real self-driving car and drive it around a test track at our lot here in Palo Alto, California, or nearby in Palo Alto. And so it's really kind of what we think of as an only at Udacity experience, that at the end of the program, you actually get to put your code on a real self-driving car, no matter where students are in the world, whether they're in the US or China or Europe or India or South America or the Middle East or anywhere else. You get to work with a team of students from all over the world and then put your code on our car. And it's a really neat experience. So let's dive into how self-driving cars work. I think of self-driving cars as having 5 key components: computer vision and sensor fusion, which are how the vehicle understands the world; localization, which is how the vehicle figures out where it is in the world; planning, which is how the vehicle decides to navigate the world. That's really kind of the brains of the car. What decisions does the car make about how to move through the world? And then finally, control, which is how the vehicle actually turns the steering wheel and hits the throttle and hits the brake in order to follow the trajectory that it came up with during the planning phase. And so we'll go through each of these components through the lens of the projects that students do as part of the nanodegree program to give you a sense of how self-driving cars work. So we'll start with computer vision. So I don't know how well this video will come across over webinar. It might be a little choppy, but this is a video of Carla, our self-driving car, driving down Highway 280 in California, in Silicon Valley. And what we do is we give the raw video feed to students, and then this is one of the projects that one of our students came up with. Two things are going on here. One, the student is using computer vision to find lane lines. And secondly, they're using, this particular student is using a neural network to draw those bounding boxes around the other vehicles on the road. And so you can see a couple of vehicles into the scene, and the neural network is trying to figure out, is this two vehicles? Is it one vehicle? Eventually they separate. Figures out it's two different vehicles, and the lane lines hold really steady even when the road is curving and the pavement changes color. And this is really impressive. It's really pretty similar to what you might see on an actual level 2 driver assistance system on the market today. And this is what students do just within the first few months of starting the nanodegree program. And it's really kind of amazing what you can do with computer vision really, really quickly. There are a lot of great tools out there, and that's part of what we teach as part of the nanodegree program. So computer vision is really how cars work with cameras to understand what the world looks like. That understanding of the world gets augmented with other sensors, in particular LiDAR, which is a term for an array of lasers, and radar are both really important sensors to also understand what the world looks like and offset some of the difficulties or the weaknesses of cameras. Cameras in particular are not great at estimating things like distance or speed or height. So if you can see this video now, this is a video of Carla driving down El Camino Real, which is the main commercial street through Silicon Valley. And this is actually some work that our team did, getting Carla to the point where she could drive on public roads. Udacity is licensed to operate Carla on public roads in autonomous mode in California. And you can see the camera feed here on the right. The camera feed is mainly looking for stoplights and determining whether the light is red or green and stopping at red lights. And then you can see this big black screen here on the left. And what you can see are these red concentric circles, and that's the LiDAR scan. And as other cars on the road pass our car, you can see these kind of blue rectangles forming, and that's the radar feedback, the ping back from the radar letting us know that other vehicles are on the road. So what the LiDAR is doing is it's using the red scan to match up to this white map. You can see these kind of white pixels from the map that has already been created. So the LiDAR we're really using for localization, which we'll talk about in a second. The camera we're really using here for traffic lights. And then the radar we're using to detect other obstacles on the road, particularly other vehicles. And that's kind of an interesting juxtaposition of how all these sensors work together. You can use sensors for all sorts of different things. You can use cameras for obstacle detection and LiDAR as well. But radar works really, really well for obstacle detection. LiDAR is super important for localization, and cameras are really important for things like classification, determining what color a traffic light is or whether a vehicle is a truck or a car, a bicycle, or something else. So that's sensor fusion, how we fuse all that sensor data together. And when we combine sensor fusion and computer vision, we get this really great picture of how the world looks. Once we know what the world looks like, now we need to figure out where we are in that world, and that's localization. So localization is the process of using landmarks that we know about to triangulate our own position in the world. Let's see, I'm having a little bit of trouble getting this video to play. When the video plays, what you can see is this is one of the simulators that we build out for our students in the nanodegree program, and they have this blue car that's traveling around, and the car is measuring its distance from various landmarks. Those are those green lines. And as the car travels around, it finds different landmarks and it measures its distance from them. And it essentially does a really complex form of triangulation using a technique called a particle filter in order to figure out precisely where it is in the world. You might think we could use GPS for this, and GPS can be helpful, but GPS often has some pretty big inaccuracies. It's accurate to maybe about 1 to 2 meters, sometimes worse in urban environments where there are really tall buildings that block the signal. And so having a high definition map and sensors that can match up what the vehicle sees nearby to the map and match precise distances allows us to do this type of triangulation that determines exactly where the vehicle is. The next step, once we know what the world around us looks like and where we are in that world, the next step is to plan a path through the world. And this is path planning. So this is another one of the projects students do in the nanodegree program. This uses our highway simulator that we built here at Udacity. And you can see this black car traveling through traffic on the highway, and you can see these green dots that stretch out in front of the vehicle. And those green dots represent the vehicle's trajectory. That's what students are building as part of this project, is they're figuring out how to navigate through traffic while adhering to speed limits and acceleration limits and jerk limits, and laying out these little pearls. They're actually called waypoints that the car needs to drive through, and that's how the car figures out how to move through the world. And it uses this technique of first predicting where other vehicles are going to be in the future, and then deciding what maneuver the car wants to take in order to navigate around these vehicles. So does the car want to stay in its lane? Should it shift lanes right? Should it shift lanes left? Should it speed up? Should it slow down? And then finally, once the car has determined what maneuver to take, it actually builds out this trajectory of waypoints in order to move through the world. So that's planning. So once we've planned the trajectory through the world, the final step is to execute it. It is done with control. And control is how we actually turn the steering wheel and hit the throttle and hit the brake to move the vehicle through the world. And what you can see here is one of our controller projects. This is a different simulator Udacity built. And this is one of our students who is trying to program a controller to follow the yellow line. You can kind of make out this yellow line. That's the ideal trajectory, the goal, target trajectory that the vehicle is supposed to follow. The green line is the trajectory that, that the controller predicts it's going to follow based on the steering angle and acceleration and brake that's being applied. So using those control inputs, the goal is to get the green line to overlap with the yellow line as closely as possible. And in fact, you can see the green line overlaps with the yellow line really, really tightly here, which is an indication of a really good controller that's following the trajectory really, really well. So that's how self-driving cars work. First, we use sensors, computer vision, sensor fusion to understand what the world around us looks like. Next, we figure out where we are in that world with the help of localization algorithms and a map. Then we plan a path through the world to get to where we want to go, subject to various constraints like speed limits and traffic signals. And then finally, we use a controller to actually execute that trajectory through the world and get us to where we want to go using steering, acceleration, and brake. So at a high level, that's what self-driving cars are, and the entire nanodegree program is kind of built to follow this pipeline. So now that you understand a little bit about how self-driving cars work, I'd like to talk a little bit about the different jobs that exist in the autonomous vehicle world. The automotive supply chain is this kind of very complex ecosystem, and it's getting even more complex as self-driving cars change the way that automotive companies relate to each other. So kind of at the center of the automotive supply chain, you can think of OEMs. OEM stands for original equipment manufacturer. You might also just call these automotive manufacturers. These are the brands that you recognize probably from driving around. So Toyota, Mercedes-Benz, Ford, Tata from India. These are companies that sell cars. They make cars and sell cars. But actually, a lot of the work these OEMs are doing, these manufacturers are doing, essentially the work they're, not essentially, but a lot of the work they're doing is pulling together parts that different component suppliers provide. So there is a giant network of what are called tier one automotive suppliers. And their entire job, these tier one suppliers, is to build parts for the OEMs. So these are companies like Denso in Japan, Continental in Germany, Delphi in the United States. Bharat Forge is one in India. And these companies, their whole job is to build different components that the OEMs then pull together to make a car. And downstream from the tier ones, you have even another layer of suppliers called the tier twos. And these are much more specialized suppliers. They're often companies that supply many different industries, not just the automotive industry. So if you think of NVIDIA, for example, who's also a great partner in our nanodegree program, NVIDIA produces graphics chips, GPUs, that are essential for lots of different industries, for gaming, for artificial intelligence, but also for automotive. And so they supply often tier one suppliers or occasionally directly OEMs. But the tier one suppliers will then package up an NVIDIA chip, say, into an automotive grade computational unit that can survive the rigors of existing in an automobile. And then that tier one will sell the solution on to the automotive manufacturer. And all of these are companies that you might want to work in if you if you are interested in self-driving cars. NVIDIA does a ton of work in artificial intelligence and autonomous vehicles. Velodyne is one of the premier providers of LiDAR units, arrays of lasers that are used for autonomous vehicles. You might recognize this here as the Android Auto logo. They do a lot of work, obviously, both in self-driving cars, but also just automotive more generally, the infotainment consoles in the center of a lot of vehicles. Bose is a tier 2 supplier doing a lot of work, mainly in sound systems. So that's kind of the traditional automotive supply chain. OEMs purchase from tier 1s, tier 1s purchase from tier 2s. But as self-driving cars change the transportation world, we're seeing new companies kind of enter the picture. So one example are technology companies. So Waymo, Apple, Samsung, Aptiv, which spun out of Delphi, all are different technology companies that are focused on largely on the software behind autonomous vehicles. And these are companies that traditionally have not been super engaged in the automotive world, but they are now spending lots and lots of money and employing lots of engineers to build self-driving cars or autonomous vehicle software or autonomous related technologies. And then, of course, even beyond the technology companies, you have the ride-sharing companies. And so these are companies like Uber and Lyft and Didi and Ola, example from India, Didi from China. These are companies that right now are operating largely with human drivers, these networks of ride-sharing vehicles that you can flag down from your phone. But all of them are looking into autonomous vehicle technology. Some of them, like Uber and Lyft and Didi, are investing very, very heavily in building self-driving cars. And so this is another type of company that you might be interested in if you were to work on autonomous vehicles. So that's a lot of different parts of the automotive supply chain, but you can think of it as this very rich ecosystem with lots and lots of different companies that you might want to work for. Everything from the brand name automotive manufacturers to the different suppliers who supply the automotive manufacturers to some of the technology companies that work in the space to the ride-sharing companies. There are a lot of different options. So the last thing I'd like to close with are just what are some of the business models that are present in autonomous vehicles? Because we can obviously think of self-driving cars, but in fact, there are lots of other types of vehicles and business models that come into play. And it's really exciting to think about how the world might change and what opportunities might open up with autonomous vehicles. So the first business model is kind of the most traditional. It's selling cars. So this is a Tesla Model S here. Tesla is currently selling level 2 autonomous vehicles. Level 2 is a terminology for driver assistance. So the driver can't just let the car drive, but Tesla does a lot with their autopilot feature to make driving the car much more automated, and the driver in many cases just has to be alert and take over when the vehicle isn't able to handle the situation. More important to our discussion here maybe is the fact that Tesla is selling cars directly to consumers. And in fact, this may be a really important business model for self-driving car companies in the future is just building self-driving cars and selling them to people the same way we build regular cars today, or companies build regular cars and sell them to customers today. Another business model is ride sharing. So we talked about that a moment ago. Ola is a ride sharing company in India. In the US, we have Uber and Lyft. In China, there's Didi. In Southeast Asia, there's Grab. There are lots of different ride sharing companies, and all of them are interested in autonomous vehicles, and many other companies outside of ride sharing, like Waymo, like some of the automotive manufacturers, are also interested in building ride-sharing networks so that you can just hail a self-driving car from your app, maybe a car that you don't yourself own. It will come pick you up, it'll take you somewhere, it'll drop you off, and then it'll drive off and pick up the next person, all without a human driver involved. And you won't own a car, you'll just subscribe to that network of vehicles. So that's another business model. A really important business model that sometimes gets a little bit overlooked is trucking. So this is a company called Embark. They actually just raised a big round of funding from Sequoia Capital, one of the top venture capitalists in Silicon Valley. Autonomous trucking could really change the face of logistics and how we move goods from one place to another. It may transition goods more from rail or from rail to a more truck-based environment. It'll allow trucks to maybe drive 24 hours a day. We may see trucks driving autonomously on highways kind of hub to hub, because highways are relatively well structured and a little bit easier to drive autonomously. So you may have hubs that are right next to highways where self-driving trucks load up, they get on the highway, they drive for hours and hours and hours, they get off the highway at some other hub, they unload, and then maybe a human driver takes the goods the last mile to to the customer's house or to the retail store. That may be kind of an intermediate step while we work on fully autonomous vehicles. But self-driving trucks are a potential game changer for I think the entire economy. A somewhat cuter type of vehicle is this vehicle. This is Starship Technologies. This is an autonomous delivery vehicle. This vehicle is designed to do something like bring you your lunch maybe. You might order lunch from a restaurant 3 blocks away. They'll call one of these little robots. It'll drive up. The restaurant will load up your lunch. The robot will drive your lunch to you, and you'll pick your lunch out, and then the robot will just continue on, and it'll all happen on the sidewalks at relatively low speed. So this is kind of, I think, a creative example of the way autonomous vehicles might change our world. A different type of autonomous vehicle technology is warehouse technology. So these are Amazon robots. And Amazon is already using robots to move goods around in their warehouses. And so you can see these giant shelves of goods that are actually mobile, because they have these little robots underneath them that drive under, lift up the shelves, and move them around wherever's the most efficient place for them to be in the warehouse. Of different warehouse technologies, automated forklifts, other autonomous vehicles within warehouses that can speed up logistics indoors and inside a facility. Another type of autonomous vehicle is mining. This mining is an environment where there are a lot of safety issues, a lot of health hazard issues. But the environment is really well contained, and so there are actually autonomous vehicles already operating in a lot of mines, driving these fixed routes back and forth from maybe one part of the mine to another, delivering goods in the mine, and it's really easy for them to do, because you just kind of map one route, and the car just kind of drives back and forth, or the mining truck drives back and forth through the mine. And then another similar type of autonomous vehicle is farming. So by some measures, there are more autonomous farm vehicles in the world than any other type of vehicle. This is a company called Mahindra in India, but John Deere in the US also working on farming. Similar to mining vehicles, you can program tractors to kind of drive routes up and down fields. And you don't have to worry about some of the path planning and perception problems that maybe you have to worry about in urban driving. It's a pretty simple procedure, but it can really make farms much, much more efficient and save farmers a lot of money and time, and allow them to take care of ever larger areas and grow more food. So these are just some of the different ways that autonomous vehicles might change the world, and I suspect we will see so many more business models. I think self-driving cars will change the world in ways we can't even imagine. It's really, really exciting. It's an amazing field to be in. The technology is so much fun to work with. It's so magical to be able to build a program that drives a real vehicle and sees the world in ways similar to the way you and I as humans can see it. It's just really a delight and an exciting place to be working right now. So that's self-driving cars, an introduction to both how they work and what jobs are available, and then how they might change the world in different ways in which self-driving cars are going to market. So I'll kind of turn things off there. I'll kick the presentation over to my colleague Jane. I think we have some questions from students that we can answer, and then maybe some live questions as well.
We do indeed. Thank you, David. We shouldn't be surprised to think that an outstanding self-driving car engineer like you can so elegantly lay out a roadmap of both the technologies and the industry ecosphere. So thank you. That was super enlightening. I'll dive right in. We've got lots of questions already that we collected both before and during now. So let's jump into some technology questions. Can you name maybe some of the most critical technologies that enabled us to actually launch self-driving cars and take them from theory into reality?
Yes. So two of the most challenging areas right now, actually three I would say, are perception, localization, and planning. And those are all things that we talked a little bit about in those slides I mentioned. So perceptions, how do you perceive the world? That used to be really the hardest part of self-driving cars. But the advances in deep neural networks, particularly a type of deep neural network called a convolutional neural network, that works really well with camera data and is starting to work with LiDAR data. That's made perception, it's helped us make great strides in perception. And so that is no longer the blocker it used to be, although there's still a lot of interesting things going on in that area. Planning is probably the most difficult area of autonomous vehicles right now, particularly for urban driving. How do you make decisions about whether to shift lanes or even predict what other objects in the world are going to do so you know how to avoid them? And then localization is this very tough problem because we're still very dependent on these high definition LiDAR maps that you need in order to localize yourself to the world. And those maps are really expensive to keep up to date because utility companies, departments of transportation, governments are constantly tearing up the roads, laying power lines, repaving them. And so it's really expensive to keep those maps up to date, and figuring out a way that we can localize ourselves in the world without a map is really, really important.
Awesome. So you talked about LiDAR, and I know this is an intro conversation here, but we've got some viewers who know a little bit about self-driving cars, I think, already, because they'd like to know if you could talk a little bit and touch on the differences between some of the sensing technologies like 3D LiDAR, 2D, solid state spinning.
Oh my goodness, lots of sophisticated LiDAR. So LiDAR is a really interesting technology that has been around for quite a while, but is really only picking up now or within the last few years because of its importance to autonomous vehicles. And it's traditionally been this very expensive technology, partly because there are very low production runs. There just wasn't a lot of demand for LiDAR units, and so to buy any one LiDAR unit was a pretty expensive process. Now self-driving car companies are buying LiDAR units in fairly large numbers, and you can see even greater demand on the horizon, and so costs are coming down quite a bit. And that's really been one of the main obstacles to LiDARs so far, has been just the really expensive nature of them. In terms of the different types of LiDARs that are available, there's solid state LiDAR, which is kind of the most advanced form of LiDAR that's currently on the market. Even it is just coming onto market. Versus a spinning LiDAR. So a spinning LiDAR is a LiDAR that literally rotates around an axis, and the beam just kind of scans 360 degrees around the vehicle. And of course, you can imagine when you're spinning something, with ball bearings around an axis, that creates all sorts of mechanical difficulties and noise in the signal. And so what everyone would like to move to is a solid state solution where you have beams kind of projecting out in lots of different directions. And those types of LiDARs are just coming online now. There's also some interesting work being done in thermal camera imaging that has some of the benefits of LiDAR, but also some of the benefits of cameras. So LiDAR in particular is really, really good at measuring distances. It works really, really well at night. Thermal cameras work really, really well at night. Cameras, very good, very high resolution, very good at classifying what types of things are. Radar, very good at measuring speed. So each sensor has kind of its different strengths and weaknesses.
Awesome. So as long as we're deep diving into the technologies here, to what extent would you say that deep reinforcement learning is being used in both the production of and the programming of self-driving cars?
Yeah, that's a great question. So deep reinforcement learning is this special type of deep learning that plays out over a much longer period. So it's you often play it like a game, and in fact, deep reinforcement learning has been really successful in training agents to play games like chess and Go. The AlphaGo agent trained by a company called DeepMind, which is part of Google now, has made some really amazing strides in this area. For self-driving cars, deep reinforcement learning has not yet proven to be that significant, although a lot of people think that may change in the future. And there are really two big reasons for that. One reason is that deep reinforcement learning is very hard to get to work. And even in simulation, companies are having a lot of difficulty getting deep reinforcement learning to work for cars. I'll talk a little bit more about that in a second. And then the second reason is, even if you can get deep reinforcement learning to work in simulation, porting that to the real world becomes a really difficult challenge. So the reason you would want to start in simulation is the way deep reinforcement learning works is you play out these long sequences where you make a decision, and then you see how that decision plays out over time. And if it plays out well, then you try and keep making more decisions like that initial decision you made. If it plays out poorly, then you stop making those kinds of decisions. And so you do that a lot in simulation, and then eventually, hopefully, you can port that trained agent to the real world. The problem is I kind of glossed over a lot of the difficulties when I said if something plays out well or plays out poorly. Defining exactly what it means to play out well or play out poorly in a driving environment is a little bit difficult. Deep reinforcement learning is notorious for the challenges involved in building the scoring or reward functions. And you can design a scoring function that you think makes sense, and then all of a sudden the deep reinforcement learning agent kind of optimizes for this really weird scenario to get the best score possible. And you don't wind up with a great driver, you wind up with a driver that kind of drives in circles or just hits the brakes and stays still, because that way it won't crash. And so figuring out how to train that agent even in simulation has been a challenge.
Speaking of challenges, you talked about some of the ways that self-driving cars actually work with the planning and the logistics. Let's go back to the controller aspect. Are there specific types of controllers and algorithms that are best suited towards self-driving cars, and what are they?
Yeah, control is this very deep field. It is the deepest of all the fields in autonomous vehicles because it's been important for automobiles, for decades, maybe even a century. Much longer than some of these other areas like perception or localization. So the most basic type of controller is a PID controller, a proportional integral derivative controller. That's a controller that every mechanical engineer would learn, as they learn to become a mechanical engineer, and that is in fact the controller that is used in a lot of applications today, including some vehicles. PID control has this disadvantage though, in that it does not model the vehicle. You should take the Nano degree to learn exactly what that means. But essentially, a PID controller is figuring out if you deviate too far from the goal trajectory, you should steer back towards the trajectory. And that's fine and well, but you don't really have a model for how the vehicle does that. You simply say, if I'm further away, go back. But you don't have this idea of what will the vehicle do if I turn the steering wheel this far to the left or this far to the right. And there are more advanced types of controllers, for example, the linear quadratic regulator and the model predictive controller that actually have models of the vehicle and allow you as a control engineer to be more precise about how to steer the vehicle or accelerate or decelerate the vehicle in order to get to that reference trajectory really, really smoothly. And so LQR and MPC, linear quadratic regulator, and model predictive control are two of the most commonly used controllers for autonomous vehicles, but there are all sorts of different control algorithms. People invent their own control algorithms, and there are other types of shape-up type controllers that engineers can use to get an autonomous vehicle to follow a reference trajectory.
So when we're talking about detecting all of these things with controllers, think of the example when I'm driving and I approach a crosswalk. I can kind of look to the faces of the drivers or the pedestrians and get a sense of whether they will cross or they won't cross. These are traditionally really difficult things for machines to do. So how do you tackle those challenges?
Yeah, that's a great question. That's more in the realm of perception. So perception and then prediction. So you're kind of touching on two different but very related topics. The first thing probably to do is to perceive what is around you, what these objects are. And it's amazing how good some companies have gotten at perceiving precisely what something is. So Waymo, if you look at some of the vehicles or some of the videos they've put out, they seem to be able to predict the age of somebody, at the crosswalk and what gender they are. And they haven't published a lot about this, but presumably they are using to then predict how quickly will they move. Are they likely to wait or to proceed through the crosswalk? It used to be the case that we would just kind of predict, is this a human or a bicycle? And even that is a hard enough prediction to make. But when you can get to the point where you can actually not predict, but perceive someone's age or gender, then you can make even better predictions about them. Once you've perceived what that thing is, then you have a model hopefully you have a model for how that thing will move through the world. So a vehicle, is probably going to follow traffic laws. A pedestrian may be less likely to follow traffic laws. Pedestrian can also move in any direction, whereas a vehicle is generally confined to basically forward and backwards with a little bit of steering angle. So you have different models for how these vehicles might behave or objects might behave in the world. So you have these two connected problems: perception, perceiving what something is, and then prediction, predicting how it will move through the world. How it's likely to move through the world.
So a lot of that is based also out of the sensors and what you detect to perceive it. So given that sensors inevitably have noise built in, how do you determine what the ground truth is when you're training the algorithms and building these models?
Yeah, so ground truthing data is in fact one of the more mundane but super difficult tasks of building self-driving cars. So typically, what you might do is you might go out and record a lot of sensor data. You might just have a human go out with a car fully loaded with sensors, and the human will drive around, and then the sensors will just record all this data. And that's great. Then you have a ton of data, but what you need to do next typically is to label that data. And somebody needs to actually look at a camera image and say, this is a pedestrian, and draw a box around the pedestrian and say, this is a bicycle. And that way you can feed that labeled data, that ground truth data, into a machine learning algorithm, which will then learn from the ground truth labels, essentially learn from the human who labeled the data, how to recognize different types of objects: pedestrians, bicycles, trucks, cars. And there are whole companies there's an industry of companies that basically takes data and labels it with ground truth measurements. Once you have those trained models, as you mentioned, there is all sorts of noise and uncertainty in the world. In perfect conditions, when it's really bright out and the camera's getting a clear line of sight to whatever vehicle it's looking at, then you might be able to feed that data into a model. And over time, if the model sees enough images of what it thinks is the same person standing at the same corner, it will be able to understand with increasing certainty what that person is, or what that object is. Although it will often express that perception in terms of certainty. So it will say, I'm 92% certain this is a person, and 5% certain it's a dog, and 1% certain it's a bicycle, or something like that. And then it will make predictions based on maybe for all three of those different objects. If it's a dog, what will it do? If it's a bicycle, what will it do? And it will come up with several different predictions about what that object is likely to do, often depending on what that object is, if it's a person or a bicycle. And so the prediction module will have these different trajectories that object might take in the future, and you track those over time and hopefully converge on a more and more certain prediction of what the vehicle is going to do. But you're dealing with all these different scenarios, and that's part of what makes autonomous vehicles so difficult. Is if you think about all these objects in the world and then predicting with various levels of certainty what they each might do in the future, you get this very dense branching of different possibilities. And so at some point you kind of have to cut that off and make a decision.
Frankly, also the hardest part about driving, figuring out what the next driver will do, right?
Right.
So speaking of challenges, what would you say the most challenging area is right now for self-driving technology at this point in time? And how long do you think it will be before we have cars on the street in just a normal, more populated way?
Yeah. Well, the most challenging area right now is probably planning. We talked a little bit before about the difficulties in perception and planning and localization, and each of the ways in which those is difficult. Perception has traditionally been very hard, but we've gotten better with the help of deep neural networks. Planning is this really difficult area because of all those branches that we were just talking about, and localization is a challenge because of mapping and how hard it is to keep the maps up to date. In terms of how soon we will start to see autonomous vehicles on the road, I really think of it as a where problem more than a when problem. So there are self-driving cars on the road today in a lot of different places. If you go to, say, Mountain View, California, where Udacity headquarters is, you'll see lots of Waymo self-driving vehicles driving around, because we actually are just about a half mile from their headquarters. If you go to Arizona, Waymo, among other companies, is doing a lot of self-driving car testing with real passengers. If you go to Las Vegas, you or I or anybody actually, at least allegedly, I have not yet done this, can hail an autonomous vehicle. There is a self-driving shuttle there sponsored by AAA and built by a company called Navia, as well as Lyft is running some self-driving cars with safety drivers in Las Vegas. Boston has done a lot of self-driving car tests because of some MIT spinouts that are located in that area. Pittsburgh similarly with Carnegie Mellon spinouts. Internationally, China has several cities where self-driving cars are in tests right now. Singapore has had a lot of self-driving cars. We're starting to see them a little bit in London and some places in Germany. Jaguar Land Rover in Europe, Mercedes-Benz. So you're starting to see them in lots of different places. And then the question is, how quickly will cars, will these geofences expand? So instead of being just in downtown Las Vegas or downtown Phoenix, how long will it be until you can drive between Las Vegas and Phoenix, say, in a self-driving car? And then the other question is, how quickly will companies start to pull the safety driver? Waymo has said they'll both start accepting the general public in their vehicles and without a safety driver by the end of this year. So it may be that by December, you or I could catch a plane to Phoenix and ride in a Waymo self-driving vehicle around suburban Phoenix. Maybe we should do that. Should we do that?
Absolutely. I'm in. Count me in. So as more and more of these cars are on the road, it's hard to ignore the question of ethics and decisions. So the philosophical trolley problem aside, how do you think ethical decision-making gets integrated into the algorithms of self-driving cars in a responsible way?
That's a great question, and it's one that self-driving car engineers have been able to get away without thinking a ton about for a while, because the problem so far has largely been just how do we get the cars to work, as opposed to how do we make particular difficult decisions. I think it probably helps to talk a little bit about the technology of how these decisions get made. They typically get made using something called a cost function. So as a self-driving car is considering various options that it might take, whether it should speed up or slow down or turn right or shift lanes left, it will often project several steps out into the future, several seconds out into the future. What might happen? What are other vehicles likely to do? What are other pedestrians likely to do? What decisions is the self-driving car likely to have to make in the future? And it will work those decisions backward and calculate a cost for each of these different options. So, what's the cost if I turn left? What's the cost if I speed up? What's the cost if I come to a complete stop? And then it will try and choose the lowest cost option. And so when we start to think about ethical decisions, what we really need to do is figure out how to program these cost functions. So if I, as a self-driving car, drive up to a stopped car that's broken down and blocking the road, what is the cost for me of slowly easing out around that car, going into the wrong lane, passing the car, and then getting back into my lane? Is that such a high cost maneuver that I'm better just staying stopped and waiting for the tow truck to come and remove that car that's blocking the road? Or is that a high cost procedure, but it's a lower cost than sitting here for 3 hours while the tow truck comes? And so I should move out around that stopped car and proceed on my journey. And so figuring out exactly how to program those costs will be, I think, a negotiation between automotive engineers, automotive business people, and government regulators. And I think automotive companies have generally been really responsible about this. Nobody wants to be unethical in these types of decisions. Nobody wants to put anybody else at risk. But there is some reliance on the general public, maybe acting through governmental entities, providing some guidance as to what you should do in complex scenarios that will help us program these cost functions better.
Yep. So we've heard about the one-off accidents, and those, of course, get a lot of attention. Two questions about that. One, how safe do you think self-driving cars are for the general public, and who takes the liability in the event of a crash or a system failure?
Yeah. So I think a few things about safety that all kind of touch on those questions. I think one is just to highlight what a tragedy it is when anybody dies, and how traumatic it is particularly for people working in this industry. I mean, that is one of the really tough things about the autonomous vehicle industry is unlike, in web software, this is an industry that really has a lot to do with physical safety, and people can get hurt, and nobody in the industry wants that to happen. And it's really traumatic and a real tragedy. Most especially for the victim and the person involved in the collision and their family, but also somewhat for the people working in the industry. Another thing to think about is just how kind of tragically common automotive fatalities are. There are about last year there were about 37,000 automotive fatalities in the United States, about 1.25 million worldwide. We're actually, for the first time in about a decade, at least in the US, seeing an uptick in automotive fatalities. People think because of distracted driving with cell phones, although people aren't sure yet. And so that's just a tremendous number of people who are dying, over 1 million people around the world every year in automotive collisions. And so the hope is that self-driving cars can become much safer and save people's lives, and but prevent some of those tragedies. In terms of who takes the liability in these scenarios, right now, it tends to be the company that is developing the software that is running the vehicle. So some companies are developing entire vehicles. Other companies are developing software. They're purchasing vehicles and then putting their own software on it. Typically, if you're running the software on a vehicle at the moment, you're kind of in control of the vehicle, and so that tends to be the entity that's most legally liable. I think over time, what we'll see is a pretty robust insurance industry grow up around autonomous vehicles. It's this whole transformation from owning a car to self-driving cars is a real disruption in the automotive insurance industry, in terms of instead of having retail customers maybe buying insurance policies, it may be that big companies that are producing self-driving cars are buying much bigger insurance policies to cover themselves as a company.
Yeah. So I'd like to pivot, if we can now, from our discussion of the technologies behind this to talk a little bit about careers in the self-driving car industry. So can you tell us a little bit about how you broke into the self-driving car industry?
Yes. I mentioned in the slides that I was a normal Silicon Valley web software engineer for about 10 years, actually, programming in Ruby on Rails. And a few years ago, I got really excited about self-driving cars, but I didn't have any background in automotive software or robotics. So I started looking around for any class I could take online that was related to autonomous vehicles. And then I started applying to every job I could find. And this was, I guess, now about 3 years ago. So it was, the industry has grown a lot. It was a much smaller industry back then. And I applied for lots of jobs, and lots of companies were not interested in talking to me because I didn't have a traditional automotive background, or I didn't have a PhD in robotics. But I got interviews at some companies, and fortunately, the folks at Ford said, there's really no reason we should hire you. You have no background in this area, but you do seem really kind of weirdly excited about self-driving cars. And they said, so, would you take a contract job? And at that point, my wife was 7 months pregnant. And they said, well, you take this 3-month contract, and if it works out, maybe we'll offer you a full-time job. And I said, yes. I said, absolutely. Whatever I can do to work on autonomous vehicles. I was so excited to work on this stuff. And I felt like if I could get my foot in the door, it would work out. And so I joined the team at Ford, and things went really well there. I love Ford. It was such a great company to work for. They have some of the smartest people I've met working on autonomous vehicles. And that led to them, offering for me to join Ford permanently, and that led to Sebastian recruiting me to Udacity to build the nanodegree program. And here at Udacity, I've gotten the pleasure and privilege of working with some of the best autonomous vehicle engineers from places like Mercedes-Benz and NVIDIA and Uber and BMW and Lyft. And all the different companies that we partner with at Udacity. And so it's been a really terrific experience in the autonomous vehicle industry for me.
That's awesome. In addition to saying yes to things that might not be your best, like what your best outcome might be in an interview, do you have any specific tips for someone who's interviewing for a job, trying to break into this field, for ways to get noticed and stand out amongst the crowd and get hired?
Yes. So I think in autonomous vehicles, it helps to have both breadth and depth, and that's probably true of almost any job that you might be looking for. And so understanding how autonomous vehicles work end to end, I think, is a real advantage. The self-driving car nanodegree is a great way to do that, but you can do that other ways too. cobble together, online courses or just read a lot about self-driving cars, watch a lot of webinars like this. And then being able to really have a passion and an excitement for a certain area of the autonomous vehicle stack, and have done a lot of projects in that area, is another advantage. And that's one reason why, as part of the Nano degree program, in fact, we have students do a whole bunch of projects. Now, in our 6-month Nano degree program, we have 9 different projects that students do in different parts of the stack, and going even deeper than that and building your own project. So maybe driving down the road, maybe have a friend drive and you hold up your camera and record a video, just like I kind of showed the video of Carla, our car, driving down the highway. You could record that for yourself, or a student could, someone interested in the industry could, and then build your own neural network to detect vehicles or find lane lines. Build your own mini self-driving car. There are kits you can build now, or you can buy now online, that will help you build a mini self-driving car, and then you can train a neural network or use other techniques to get it to, say, follow a line of tape around a room. There are lots of different projects like that. They're publicly available academic data sets you can download and do interesting things with LiDAR data, radar data, camera data. I think finding that area you're really excited about will really help you stand out and help hiring managers know where to put you and where you're interested in being. That said, you also kind of have to be willing. I think it helps to be willing to say yes to wherever you should go. So, for example, when I went to Ford, they said, "What do you want to do?" And I said, "I really want to be a perception engineer. I want to work on deep neural networks for self-driving cars." And they said, "That's great, but where we really need help right now is on our computational hardware team." And I said, "Great, I'm happy to work on that too. Like, whatever." Well, I didn't say whatever, but I said I am thrilled to work on computational hardware. And I was so excited to get that opportunity. And so I think, having an area you're passionate about is really, really important, but then also being open to opportunities when they present themselves, even if they're not exactly what you planned for yourself, I think is also really important.
That's awesome. It's hard not to appreciate your enthusiasm for this field still now, which is wonderful.
A lot of
So you talked about the Nano degree program. 2 questions. One, what are the prerequisites for someone who might not have experience in self-driving cars, or even artificial intelligence or neural networks, before they take the Nano degree program? What should they know, and what do you expect that they know? And what is the main goal in the Nano degree program? Like, what does someone leave with?
Yes, so we actually have 2 different Nano degree programs in this space, so I'll talk about each of them. One is our Intro to Self-Driving Cars program, and the other is our Self-Driving Car Engineer program. The Self-Driving Car Engineer program is a more advanced program that's designed to take a student who already has programming experience and a basic engineering background and train them to become an autonomous vehicle engineer by walking through the different areas of the self-driving car stack, some of the ones I showed in my slide deck, plus some other areas, and building up those types of projects where you're doing things like finding lane lines or building a path planner to navigate through highway traffic. And the end goal is that you have, as a student, this great portfolio of projects that you can take to an employer and show that you've done all these different things across the self-driving car stack, and maybe even gone extra deep in 1 or 2 areas that you're really excited about, and gone beyond the minimum project requirements and built a really terrific project in a certain area. Then the prerequisites for the self-driving car engineer program are intermediate level programming ability, ideally in Python or C++, since those are the 2 languages of the automotive industry or the autonomous vehicle industry. Python more for machine learning, and C++ more for system software and code that goes on the vehicle. And then basic physics, basic linear algebra, basic calculus, basic statistics. So things like trigonometry kind of come back to haunt software engineers like me, who kind of forgot about them in high school. Some of the mechanical engineers who are already in the automotive industry and looking to learn more about autonomous vehicles, they know all about trigonometry and physics and mechanics. Linear algebra, something that as a software engineer I've used off and on, but something that sometimes mechanical engineers or other types of engineers aren't as familiar with. And if you're not familiar with any of those areas, we have our Intro to Self-Driving Cars program, which is a shorter program. It's only 4 months compared to the 6 months for the full Self-Driving Car Engineer program. The Intro to Self-Driving Cars program is designed to train anybody up in those prerequisite areas, in Python and C++ programming, in calculus, linear algebra, statistics, physics, all those different areas of core engineering and software programming that you need in order to become a self-driving car engineer. You can start with Intro to Self-Driving Cars. Anybody is eligible to start that program. And then once you graduate that program, you'll know everything that you need to know in order to jump into the self-driving car engineer nanodegree program.
That's awesome. So one of our viewers has asked, are there any hardware projects integrated into the self-driving car nanodegree program?
Yes, so we have one hardware project, you could call it a hardware project, arguably, that I mentioned at the very beginning of the presentation that I never got back to. I apologize, I should have highlighted that more fully, which is putting code on Carla, our self-driving car. So the very final project of the self-driving car engineer nanodegree program is putting code on Carla. Students form teams of about 5 students each. With other students, it can be students all around the world. You can find students that are just in your country or time zone. And you write code that goes on Carla to drive Carla around a test track on our test lot, and then use the actual camera in Carla to detect a traffic light, classify the traffic light, stop when the light's red, go when it's green. And it's kind of amazing. You kind of start with that in simulation. Then once you get everything to work in the simulator, you send your code to us here in California. We run it on our simulator just to make extra sure everything works. And then once everything works, we put it on the vehicle and we send you a playback of how your code runs on the vehicle. And if it needs a little bit of tweaking, you can tweak it, send it back to us. We'll run it again on the car. Once a month, actually this Friday is one of those days, we invite anybody in the area to come to our test lot. And if they want to see their code run on the car and do some debugging live with the vehicle, they're welcome to do that. So that's kind of the main hardware project in the nanodegree program. We have other nanodegree programs at Udacity, most notably our robotics software engineer nanodegree program, where you can actually buy a system on a chip. So in that particular program, robotics, you get a discount to buy an NVIDIA Jetson TX2 system. And you can buy that and train neural networks to do robotics types of projects on that system. In the self-driving car program, we're mostly operating in simulation and in development on your local machine or in the cloud, but then you actually get to put code on hardware at the very end in that capstone project.
I remember meeting the team that won the competition for the very first, and it was amazing because first of all, they were from all different parts of the world. It was the first time they actually met each other in person, and then they actually got to see their code run on Carla. So it's an incredible program to work remotely with people around the world on an actual car that's running on an actual track. So it's incredible. We only have 3 more minutes left, so I wanted to touch on something I think which is important is what is the value of the nano degree in the eyes of the hiring managers and the partners that you see? And if you can share with us some of your success stories, what have some of the students done and what kinds of jobs have they gone on to accept?
Yes, this is one of the things I think we're really, really proud about of the nanodegree program is that almost every employer that we know now is familiar with the nanodegree program. This is, I think, considered like the kind of most common and probably the best way to learn about self-driving cars now. And if you take your resume to companies and say, I completed the Udacity self-driving car engineer nanodegree program, that really means something. Employers have an understanding of the breadth of topics that you cover and the number of projects that students have done as part of the nanodegree program. And so we're really excited about that, and it's been really helpful to students as they apply for jobs in the industry. We have a lot of different success stories. We have students who work at almost every self-driving car company you can imagine. We also have a lot of students who come from those companies, and they may already even be working on self-driving cars, but they say, I'm working on one particular area. I know a lot about, say, localization, but I'd love to learn more about perception or control, and so that's why I'm taking the nanodegree program. So we have, for example, George Sung was one of our very first students in one of the, I believe, the very first class of graduates of the self-driving car program. And before he even graduated, he landed a job at BMW. He had been an engineer at a chip manufacturer, just working on building faster computational chips. And then he got a job largely through the nanodegree program and also his own efforts at job hunting and interviewing. He said he applied to 90 jobs, but he got a job at BMW working on their deep learning team, and he's been there for about a year. We have a number of students who've been hired on to the deep learning and autonomous vehicle teams at NVIDIA, who's been a great partner of ours. We have students who work at automotive suppliers like Delphi and Aptiv and Continental. We have students who work at manufacturers like Mercedes-Benz and Volvo. A number of our students have been hired onto the autonomous vehicle team at Lyft, who's been a great partner of ours, particularly for the intro to self-driving cars nanodegree program, working on everything from perception to localization. We had a path planning challenge with Bosch, who's one of the biggest automotive suppliers in the world, actually the largest automotive supplier in the world based out of Germany. And a number of our students work at Bosch on planning and on other teams there. So we have students all over the place, and we're really, really excited about the contribution of our students to the autonomous vehicle world and their ability to then hire more Udacity students, because they understand as well the value of the education they got through the nanodegree program, and they're really excited about hiring more students.
Awesome. David, thank you for all of your help. We're out of time. I wish we had more time because we have a ton more questions. People are interested in open source projects they can contribute to and books that they can, so maybe we can follow up with some resources in the follow-up emails we send to give people some ideas on where they can look for these things. But thank you so much for all of this enlightening information. Thanks to all of you who joined in with us today. This is one in a series of webinars that we do on professional development. Check the links for some upcoming webinars that we have on other topics. And David, thank you for spending this hour with us, teaching us about the technology, the career opportunities, and just the field of self-driving cars. If any of you are interested in learning more about Udacity self-driving car nanodegree programs that David talked about today, check the link in the chat. And we're out of time and overtime, so stay curious, keep learning, and see you all next time. Thanks, David.
Bye-bye.